Welcome, welcome, welcome. Oh man, I haven't checked to see whether my stuff is going to show up. Darn it. Okay, well, hopefully everything works swimmingly today. Today, on Mind of Meaning, we're going to go through Khan Academy stats. Now, I know in the past stream, we were going to go and do the MIT course, but because I can't stay focused on anything for that long, today I want to go through Khan Academy, and we'll probably come back to this. You know what? Actually, I changed my mind because we were going to finish this up. We were going to finish. I feel like I came off a little aggressive there. Just like, let's do it! But no, I'm just, caffeinated. Relax. Relax. Hi. Welcome. Thank you for joining me. Today, on Mind of Meaning, we're doing stats and probability so that we can understand the world better and not be fooled and think well and be well. And we, at this channel, want to examine different ways of knowing. Ways of knowing, that's the key phrase. Ways of knowing. And we're doing that initially through stats and probability because, frankly, I don't understand it as well as I should. So, we're going to do stats and probability. Do you like my little mask guy here? Yeah. He's just there to keep me company, you know? But, stats and probability as a way of knowing, we're going to get into it right now. We're finishing up this first section of the MIT course, and then we're crushing Khan Academy. Stats and probability. Let's go. So, if I remember correctly, where we left off was a discrete example right here. Now, am I going to learn everything about this right now? No. We're probably just going to watch the video. And then we're going to move over to Khan Academy once we're done with all of this. Then we'll probably take a step back and go through the supplemental material. But right now, we're getting into it. Right now.
Let us now move from the abstract to the concrete.
Can you hear that?
Recall the example that we discussed earlier, where we
Was
have
I blowing
two
out
rolls
my
of a
microphone? Oh man, I was
tetrahedral die,
shouting really
so
loud.
there
I
are
might have been
16
blowing out my
possible
microphone.
outcomes
I apologize. I really apologize for screaming. But anyway, let's get into it.
illustrated in this diagram. To continue, now we need to specify a probability law, some kind of probability assignment. To keep things simple, we're going to make the assumption that the 16 possible outcomes are all equally likely and each outcome has a probability of 1 over 16. Given this assumption, we will now proceed to calculate certain probabilities. Let us look first at the probability that x, which stands for the result of the first roll, is equal to 1. The way to calculate this probability is to identify what exactly that event is in our picture of the sample space and then calculate. The event that x is equal to 1 can happen in 4 different ways that correspond to these 4 particular outcomes. Each one of these outcomes has a probability of 1 over 16. The probability of this event is the sum of the probabilities of the outcomes.
Hold on, I forgot to bring up my handy dandy notepad here. My handy dandy notepad. Alright, so... Oh, darn it. Okay. Listen, relax, okay? I don't need your judgment. People. I don't need your judgment. Alright, we're gonna call this stats and probability. What number are we on? I think this is notes number 5. Stats and probability notes number 5. saving it as such. You can't see any of this right now, I know, but you know. Soon enough, my people. Stats, notes, 5. Soon enough. All right, welcome back. Thank you for joining me. We're getting back into this high quality content. High quality content. The best. Literally. The best content on the internet right now about stats and probability. That's me. As you can tell. All right. Let's get into it here.
Outcomes that it contains.
All right, so if you're just joining us, which I know you're not, but if you were joining us and I watched one of those YouTube videos, it's like tries to tell you how to do YouTube well, right? And I have to play to the audience that I want as if you're there. So I'm pretending that you're there right now. Okay. And like I said, high quality probability stats content is what I offer. And right now what we're doing is an MIT course on probability because the stats course was too hard, but we're gonna get to that one. Okay? We're gonna get to it. But right now we're doing the probability because it was a little more elementary. But it's still MIT, so it's still like challenging in theory. So we're just we're finishing up where I was last time. This is a discrete example on the course. We're still in the first section here. And like I said, we're going to be moving over to Khan Academy after we're done finishing up this section. We're going to crush Mr. Khan's Academy. Okay, so let's get into it. Here we've got a probability. So this is an example, a discrete example, discrete versus continuous, because discrete sets are like sets that are like individual units. It doesn't account for infinity or something like that. That's sort of my basic understanding. And we're gonna just listen to what he has to say. So I'm just trying to review in my head. Last time we covered axioms. The axioms of probability. One, that all probability has a non-negative, is non-negative. Two, that it's normalized, that is, I think it can be, I think that meant something about like it can be set to be between 0 and 1, I think. Any probable thing. I mean, if I'm honest, I can't really remember. You know what? Why don't we just to like refresh, because this is an important part. So I want to refresh. I know I have the notes, but you know, I'm here. We're here. We're having a good time. I'm well caffeinated. Probability axiom. So let's just remind ourselves. Actually, I can probably just dig into the transcript here. Okay, hold on. Oh, there it was.
Let event A did.
Okay, so there was a
and we capture this
set.
certainty by saying that the
Non-negative.
probability of event omega is equal to 1.
So the probability of the entire set of possible things was 1. Okay, so let's you know what? Just to get this really firmly in our head, what I want to do... Yeah, I know... Listen, stop judging me, okay? I know I'm all over the shop. But this... Oh, man, it's raining. This is an important piece of information, okay? Important piece of information. So we're digging into it. That's very attractive. Okay. What we're going to do is watch a couple other videos. Oh, hey, look, I'm live. Oh, yeah. Okay. Probability axioms. Ooh, explained. I know you can't see anything right now. I'm gonna bring that puppy back up. Here we are. Any of this Who do we trust on the internet? Who do we trust? Who do we trust? Electrical lectures, probability models and axioms is a live course from 10 years ago. Axioms of probability, Trev Tutor. Axioms of probability, Akita Gate. Yeah, my vidIQ stuff is popping up, so I can't really see it. No one's really doing this well. Like, these thumbnails are not clickbaity enough for me to want to click into it. Zed Statistics, he's pretty engaging, but this isn't about what I'm looking for. Stats for everyone. Okay, listen. Okay, so here's what we're gonna do. We're gonna see what the internet was like 9 years ago with probability axioms. Then we're gonna pop over to stats for everyone. This was only 1 year ago. I don't even know if this person still makes content. We're gonna find out. We will find out. You and me, best buds for life. If you're enjoying this content, consider supporting me on Patreon at patreon.com/mindofmeaning. That's patreon.com/mindofmeaning. This is the most engaging, thorough, scatterbrained, like a scatter plot, statistics and probability information on the web. That's not entirely what this channel is about. Once again, this channel is about ways of knowing, how we know things. And stats and probability are a way of knowing things. They're extensions of math, right? Gambling, we don't gamble here, but it's fun to think about, right? So stats and probability, most engaging content on the internet. And if you feel like supporting me, go to patreon.com/mindofmeaning. And we will greatly appreciate your support. All right, so stats for everyone. What was their most recent thing? They got 477 videos and they have 8.82K subscribers. That feels criminal. But they were available just 1 month ago. So let's see where they were at 9 years ago. Oh wait, that's the other lady. So we're gonna watch this old one first, probability course, and we're gonna see how they do.
Hello, in this video I would like to talk about random experiments and probability axioms.
Okay, that microphone is garbage, so we're just not gonna watch that because I just can't deal with that. We can do better. Come on, stats for everyone. I believe.
In this video, we're going to discuss the
much better.
3 axioms for probability.
I'm ready.
And this is the definition of probability. So, this sets the stage for everything that we know about probability. Later, when we do proofs, we'll refer back to these axioms. So, while it might feel like right now, why do I care about these axioms? Later, you're going to realize that these are extremely important for basically understanding anything about probability. Okay?
Thank you.
So, starting with axiom 1. Axiom 1 states that basically probability of an event must be positive. Okay, so let me write that down.
Must be
for
positive.
Every
Don't forget it.
Event.
Don't forget it. Must be
positive. The event A. The probability of that event has to be greater than or equal to 0.
Greater than or equal to 0.
So it can equal 0, but it may not be negative, right? Probability has to be positive or 0.
Positive or 0.
Axiom 2.
Axiom number 2
states that the probability of the sample space.
The probability of the sample space.
For the sample space.
For the sample space.
I'm going to use this notation S, capital S. So for the sample space, the probability, the total probability,
equals 1.
Right? So Let me go ahead and write this. This is basic.
So, axiom 1. For every event, A, meaning any event, meaning A, meaning any event, meaning A, the probability of A has to be greater than 0, or 0, equal to or greater than 0. Axiom 2, for the sample space, S, the probability of S being the entire space of the sample. That is every sample that you spaced samples. For that, the probability of it has to equal 1. It has to equal 1. This is what we learned about in the previous lesson with MIT. We learned that the sample space was 1. Because this is the normalization axiom. We've collected the data. We've put it all together. We have some sample of people, and the totality of that has to be 1. It has to be. Why does it have to be? Well, we learned that you have some set, right? That set. And you're trying to examine a subset of that total set of the space that you sampled. You want to look at a sample of that total, a subset of that total sample. It has to be 1. How do I get into more detail about that? What does it mean to be greater than 1? Or what would it mean for the sample space to be greater than 1? Let's think about it for a second. Why can't it be greater than 1? Well, we don't know anything outside of it. The sample space is the constraints. It's what we've done. It's what we've observed. We can't talk about things we can't observe. We haven't observed. We can infer things, and that's kind of the point of statistics to begin with. But we can't say for sure. We can only talk about what we have. And what we have is the totality of what we have. And we just... Normalization. Are you familiar with this word? My understanding of this word, normalization, is basically you... It's like conventionalizing stuff. So you have all this stuff. It's in different varieties of... So like... I think normalization when it comes to like data analysis is like when you have all this data, it's in different formats and different styles, and like say you have numbers, right? And some ages say like, you know, this person is 15.45 years old. This one says this person is 17 years old. This one says it's 16.1 years old. This one says it's 54.5 years old, like with a little half. So normalization in that context would be like, okay, we're just going to say that a person is the age that they are, right? So they're 15, they're 16, they're 54, they're 192. All right, that's integers, baby. Integers. That would be normalization, right? We've set them all to be one kind of number. There's no 1/2. There's no what do they call it? Floating points. It's all just integers. We've normalized it. We've made them all conventionally the same. We followed one convention, one standard format of presenting the data. So that's what we're saying here. We have normalized the data. We've taken our sample and we have oriented it towards the context of saying that the entirety of the sample is equal to 1. So everything that we've collected is interpreted through the context of calling it 1 or less than 1, because it's just a way of thinking about it that makes it easier to think about. Have I been repetitive enough for you? Have I given you incentive to internalize this information? All right. So, axiom 1. Every event A, the probability... God darn it. Come back to life. Bring me back. Okay. Every event A, the probability of A has to be greater than or equal to 0. That's, what's it called? Okay, we can go back over to MIT. That's called the axiom of non-negativity. Axiom of non-negativity, number 1. Axiom of non-negativity, number 1. Axiom number 2, the axiom of normalization. Everything, every sample space is in relationship to 1, so that we can understand it. And axiom number 3,
that
coming down the
total probability is 1. All right, that's basically what axiom 2 is stating. All right, and then lastly, axiom 3. Axiom 3 has to do with disjoint events if we were to take their union. Okay, so for every,
I remember this. It was for every, oh my goodness. I haven't studied since the last time you were here. So the stuff isn't at the forefront of my head. So let's see if I can remember it. For every, what was this axiom? I think this had to do with when you had a union of two things, those things that are unified. That is, if you imagine a Venn diagram within a sample space. So you have the sample space that's like a rectangle, and then you have like a Venn diagram within that sample space. So two circles put together. I forget if this had to do with if they were disjointed. Okay, it's starting to come back to me. If they were disjointed, if they were not unified, if they weren't connected, but in fact, this was on this side of the rectangle, this circle was on this side of the rectangle, then the entirety of the union of that probability would be this one plus this one. I think that's what this axiom was called. And then if they were unified, it would be this one. I mean, this is like basic arithmetic stuff, right? It would be like this one, the entirety of this one, plus this one minus the difference of the overlap. I think that's what it was. Anyway, let's let her tell us.
Infinite.
For every
infinite sequence.
Infinite sequence.
Disjoint.
Disjoint.
Right. What does disjoint mean? Disjoint events.
Non-unified.
Right. So remember, disjoint means that the events have no elements in common. Right. So if we have event A1, A2, ... none of these events have any elements in common because they are all disjoint. Right. If I wanted to find the probability
blasting you out right now, I'm sorry.
Of the union, right? The union of all of these disjoint events, right? This is equal to the sum.
The sum
of the probability for each event.
The sum of
so
the
just
probability
in case you're not familiar with
each
this
event.
Notation here.
Teach me.
Basically what I'm saying is the probability of
A1,
union A2, union A3, union ... all the way. It's infinite sequence, so all the way to infinite.
Sequence,
right?
All the way
Equals
to
the probability of A1 plus the probability of A2 plus the probability of A3 plus ... forever. Right?
Forever.
All right. So we are going to be using these 3 axioms in the next few videos.
Okay. The MIT guy was a lot more clear, not gonna lie, but he's the MIT guy. I'm sure this lady goes into more detail. I just wanted a little bit of a refresher, okay? And we've been refreshed. Are you feeling refreshed? I'm feeling refreshed. So now we're gonna go back. We're gonna go back to our discrete example, which I think I was in maybe, but then I clicked away from. We're starting from the beginning. We'll do it live. Make that big.
Let us now move from the abstract to the concrete.
Bring up my handy dandy
Recall
notepad.
the example that we discussed earlier, where we have 2 rolls of a tetrahedral die, so there are 16 possible outcomes illustrated in this diagram. To continue, now we need to specify a probability law, some kind of probability assignment.
All right, so let's examine what we have here. We've got 2 rolls of a tetrahedral die. I have some tetrahedral die somewhere, but I don't have it with me right now. I'm gonna have to dig those out. I've got a bunch of different dice because I'm a nerd and I used to play the D&D, but it's a whole different story. So I've got a bunch of dice. We're gonna bring that out at some point, not right now. Let's see what else he has to say.
To keep
Also, if you have something to say, chat me. Put it in the chat. If you're here, just, write me a little chat. Otherwise, I'm just talking to nobody. Nobody, okay? So, write a little thing in the chat. If you want, go to my Patreon. I'm not going to say you're a bad person if you don't go to my Patreon, patreon.com/mindofmeaning, and subscribe. I'm not going to say you're a bad person if you don't do that. I'm just going to say that, if you do that, you're a good person. You're a better person than the person who doesn't do that. Okay? So, I'm letting you know that. Okay? Otherwise, just leave a chat in the little chatty, and maybe we'll have a little talkie about this exciting material. Okay? So right now, a discrete example. He's got tetrahedral die. Y equals second roll, X equals first roll. And we're going to be examining the chances that any... we might have even watched this video, but we're going to watch it again.
Being simple, we're going to make the assumption that the 16 possible outcomes
every
are
possible
all
outcome have a
likely,
probability
and each outcome has
1 out of
a probability
16.
of 1 over 16. Given this assumption, we will now proceed to calculate certain probabilities. Let us look first at the probability that x, which stands for the result of the first roll, is equal to 1. The way to calculate this probability is to identify what exactly that event is in our picture of the sample space and then calculate. The event that x is equal to 1 can happen in 4 different ways that correspond to these 4 particular outcomes. Each one of these outcomes has a probability of 1 over 16. The probability of this event is the
Tetrahedral die, that's 4. Oh, did I just break my thing?
It is of the outcomes that it contains, so it is 4 times 1 over 16.
Yeah, it's not showing up. Ugh. Hold on. I think it's working now, maybe?
Equal to 1/4.
It's too early for you to start messing up, okay? I can't deal with it. Okay, so we're gonna just... My CPU usage seems fine. We're going to pop this puppy up. Still not working. Great. Love that for me. You know, I slammed my hand down on the table once and now it's getting all problematic. Okay, so here's what I'm going to do. I'm going to do that, and then I'm going to do that. There we go. I think we're good again. Ay, ay, ay. Okay, so as I was saying before I was so rudely interrupted, it makes sense, right? 4 out of 4, 4 times 4 is 16. So here we have 1, 2, 3, 4. The amount of numbers on a tetrahedral die, right? So there's a 1 in 4 chance that we're going to get 1, 2, 3, or 4.
Let now z stand for the smaller of the two numbers that came up in our two rolls. So for example, in our picture of the sample space, and then calculate. The event that x is equal to 1 can happen in 4 different ways that correspond to these 4 particular outcomes. Each one of these outcomes has a probability of 1 over 16. The probability of this event is the sum of the probabilities of the outcomes that it contains, so it is 4 times 1 over 16 equal to 1/4. Let now z stand for the smaller of the two numbers that came up in our two rolls. So for example, if x is 2 and y is equal to 3, then z is equal to 2, which is the smaller of the two. Let us try to calculate the probability that the smaller of the two outcomes is equal to 4. Now, for the smaller of the two outcomes to be equal to 4, we must have that both x and y are equal to 4. So this outcome here is the only way that this particular event can happen. So since there's only one outcome that makes the event happen, the probability of this event is the probability of that outcome and is equal to 1 over 16.
Okay, that tracks.
For another example, let's calculate the probability that the minimum is equal to 2. What does it mean that the minimum is equal to 2? It means that one of the dice...
Yeah, it means at any given point, when you roll the dice, you have 2 chances to make it to the top. Do not miss your chance to roll. Okay? You have 2 chances to roll a 2. You have the first chance, you have a 1 in 4 chance. You have the second chance, you have a 1 in 4 chance. What does that equal? What does that equal? You have a 1 in 4 chance the first time and a 1 in 4 chance the second time. That equals 2 opportunities out of 16 potential options. That's going to be 2 out of 16, I believe, right? At least one has to be 2. That is, at least one roll has to be 2, so that's 2 out of 16 chances. Or 1 out of 8. An eighth, I think. If my math isn't mistaken, and it very likely is, but we're going to see what he has to say.
Resulted in a 2, and the other die resulted in a number that's 2 or larger. So we could have both equal to 2. We could have x equal to 2, but y larger, or we could have y equal to 2 and x something larger.
I didn't think about
this
that.
This green event, this green set, is the set of all...
So I was actually wrong, because I wasn't factoring in what he was actually saying, which was, we can't think about things that are less than 2. 2 has to be the minimum. So it can't be anything less than 2, i.e. 1. It can't be 1 It has to be 2. 2 has to be the minimum. That's what we're trying to figure out. When is 2 going to be the lesser of a situation? It doesn't matter what the other one is as long as it's greater than 2. 2 or greater. If they're both 2, then the minimum is still 2 because the minimum is 2. That's all there is to choose from.
Outcomes for which the minimum of the two rolls is equal to 2. There's a total of 5 such outcomes. Each one of them has probability 1 over 16, and we have discussed that for finite sets, the probability of a finite set is the sum of the probabilities of the elements of that set. So we have 5 elements here, each one with probability 1 over 16, and this is the answer to this problem. This particular example that we saw here is a special case of what is called a discrete uniform law. In a discrete...
Hold on. Remember? Oh, what is going on? What was that? Anyway, remember what I said last time about jargon? This feels like jargon. This is important. Okay? Discrete uniform law. That last thing we saw was where it was 5 times 1 over 16. Because there were 5 opportunities to get 2, where 2 could be the minimum, right? So you multiply that by the 1 over 16, which is means the totality of the thing itself, right? So discrete uniform law. That last example was an example of this discrete uniform law. Hold on. Assume, what is that, omega? I always forget the name of these. Okay, assume, I remember what it means. It means the total set consists of n equally likely elements. Assume A consists of k elements. So A is the sample set of the total set. So assume the total set consists of n equally likely elements. And you've got some sample space, A, which consists of k elements. What is the probability of A that A equals... Are we muted? We're muted. Why did I mute it? Stop it. Oh my goodness. We're going to get through this, guys.
Which is finite.
Finite.
And it has n elements. And we assume that these n elements are equally likely. Now, since the probability of omega, the probability of the entire sample space, is equal to 1,
omega, it was
this
omega.
means that each one of these elements must have probability 1 over n.
1 over n.
That's the only way that the sum of the probabilities of the different outcomes would be equal to 1 as required by the normalization axiom. Consider now some subset of the sample space, an event A that has...
What did he just say?
B equal to 1 as required by the normalization axiom. Are equally likely. Now, since the probability of omega, the probability of the entire sample space, is equal to 1, this means that each one of these elements must have probability 1 over n. That's the only way that the sum of the probability...
Okay, so what's happening here? Why does it have to be 1 over n? Well, n means the total number of things in the omega, the total set, right? So the normalization axiom he's bringing up here, because each one of these little tiny pieces would add up to n. We have n elements, which in theory means more than one element, right? But the total number of elements, there is some total number of elements, so whatever element that is being represented by the fraction here, assuming we've surrounded one with our subset, if we were to make the entire thing, it would have to equal the total number, which was n elements. N elements consists of n. So the numerator would have to equal the total number of discrete whatevers. And that's why this gets normalized, because once that would happen, it would be n over n. If we encircled the entire thing, it would be n over n. That would equal 1, and thus normalized. You got it. You're a genius. You are a genius. Thank you for joining me. Thank you for being a genius. And you know what else is genius? You know what else? Going to patreon.com/mindofmeaning and contributing 1 latte worth of your hard-earned money that I respect. I respect your hard work. And if you could contribute a latte's worth of money, that is $5, just $5 to this content, I would be forever in your debt. I mean, not really, but I would appreciate it, is what I'm trying to say. I would appreciate it. He would appreciate it. Look at him. He's old. This is me in the future. This guy. It's me. Okay? I want him to have a good life. Don't you want me to have a good life? I'm just kidding, but I'm serious. Okay.
Probabilities of the different outcomes would be equal to 1 as required by the normalization axiom. Consider now some subset of the sample space, an event A that has exactly k elements. What is the probability of the set?
Look, I know it's dry. I know it's dry. I know it's dry. But this is important stuff. This is about learning about the world. It's about knowing things. And sometimes life has boring stuff. And that's just the way it is. But if you want to be informed, sometimes you just have to get through it. And maybe you find this exciting. Maybe this is the best information you've ever consumed. And if so, that's fantastic. And I'm happy to be the arbiter, to be the conveyor, to be the avatar of the presentation of this information to you. So let's continue.
A, it's the sum of the probabilities of its elements.
Yeah,
There
yeah,
are
we got
k
that already.
Elements,
There are k
and
elements,
each
blah,
one
blah,
of them
blah.
has
Each
a
one of them
probability of 1
of
over n.
1 over n.
And
Yeah,
this
k
way
elements
we can
within
find
a...
the probability of the set A. So
Yeah.
when we have
Yeah,
a
yeah,
discrete
we got that.
uniform
We're geniuses.
probability law, we can calculate probabilities by simply counting the number of elements of omega, which is n, finding the number n, and counting the number of elements of the set A. That's the reason why counting will turn out to be an important skill, and there will be a whole lecture devoted to this particular topic.
Okay, you hear that? We're going to learn to count. Love that for us. On to the next piece of riveting information. We're going to a continuous example. Continuous meaning infinite, related to the infinite, meaning it is not discrete, meaning it is not self-contained, meaning we're getting connected to the one, getting connected to the infinite. All right, join me, join him. We're doing it. We're getting into it here. We are staying so awake, so awake. All right. You know what I'm going to do for this one? I'm just going to lay back with my notes because I want to get to Khan Academy, but I also want to finish this up. And I keep interrupting myself. So let's do it.
We will now go through a probability calculation for the case where we have a continuous sample space. We revisit our earlier example in which we were throwing a dart into a square target, the square target being the unit square, and we were guaranteed that our dart would fall somewhere inside this set. So our sample space is the unit square itself. We have a description of the sample space, but we do not yet have a probability law. We need to specify one. The choice of a probability law could be arbitrary. It's up to us to choose how to model a certain situation. And to keep things simple, we're going to assume that our probability law is a uniform one, which means that the probability of any particular subset of the sample space is going to be the area of that subset. So if we have some subset lying somewhere here, and we ask what is the probability that we fall into that subset, the probability is exactly the area of that particular subset. Once more, this is an arbitrary choice of a probability law. There's nothing in our assumption so far that would force us to make this particular choice, and we just use it for the purposes of this example. So now let us calculate some probabilities. Let us look at this event. This is the event that the sum of the two numbers that we get in our experiment is less than or equal to 1/2. It is always useful to work in terms of a picture and to depict that event in a picture of the sample space. So in terms of that sample space, the points that make this event to be true are just a triangle that lies below the line where this is the line that x plus y equals to 1/2. Anything below that line, these are the outcomes that make this event happen. So we're trying to find the probability of this red event. We have assumed that probability is equal to area. Therefore, the probability we're trying to calculate is the area of a triangle. And the area of a triangle is 1/2 times the base of the triangle, which is 1/2 in our case, times the height of the triangle, which is again 1/2 in our case, and the end result is 1/8. Let us now calculate another probability. Now this is an event that consists of only a single element. We take the point 0.5, 0.3, which sits somewhere here. The event of interest is a set, but that set consists of a single point. So we're asking for the probability that our dart falls exactly on top of that point. What is it? Well, it is the area of a set that consists of a single point. What is the area of a single point? It is 0. And similarly, for any other single point inside that sample space that we might have considered, the answer is going to be 0. Let us now abstract from this example, as well as the previous one, and note the following. Probability calculations involve a sequence of 4 steps. Starting with a word description of a problem, of a probabilistic experiment, we first write down the sample space. Then we specify a probability law. Let me emphasize again here that this step has some arbitrariness in it. You can choose any probability law you like, although for your results to be useful, it would be good if your probability law captures the real-world phenomenon you're trying to model. Typically, you're interested in calculating the probability of some event. That event may be described in some loose manner, so you need to describe it mathematically. And if possible, it's always good to describe it in terms of a picture. Pictures are immensely useful when going through this process. And finally, the last step is to go ahead and calculate the probability of the event of interest. Now, a probability law in principle specifies the probability of every event, and there is nothing else to do. But quite often the probability law will be given in some implicit manner, for example by specifying the probabilities of only some of the events. In that case, you may have to do some additional work to find the probability of the particular event that you care about. This last step sometimes will be easy. Sometimes it may be complicated, but in either case, by following this 4-step procedure and by being systematic, you will always be able to come up with a single correct answer.
Not a whole lot of certainty in life, but probability is certain. Or is it? countable additivity and interpretations and uses of probabilities. So we're going to crush these last two lectures here in the next 10 minutes or so, assuming that they're less than 10 minutes. And if not, we will just go a little bit over time. And then we're moving to Khan Academy. Thank you for bearing with me here. I am doing my best here to give you the best probability and statistics content that has ever existed and will ever exist, okay? And remember, this is not a probability and statistics channel. This is a channel about ways of knowing, of which probability and statistics are a part. We trust math. We love math. Math loves us. And we're learning it. For the sake of understanding, in particular, things like studies, research that entail probability and statistics. Things that I don't personally understand that well. And we live in a world full of hard to understand information. But just because information is hard to understand doesn't mean that there isn't some truth to it. And how do we discern conflicting studies with each other? How do we know which one to trust and which one not to trust? Well, that's part of what I'm trying to figure out here, because I don't know. I don't know how to judge one study from another. I don't understand how these things really work. I'm working on getting the smarts, right? And I don't want you to feel ashamed if you don't get it, because it's complicated unless you're into this sort of thing. So I want you to join me. Join me on my adventure. And if you're feeling generous, if you're feeling so kind, please consider going to patreon.com/mindofmeaning and contributing. Just, $5, just a little $5 amount once a month. Support the channel, support me, support yourself, support this content. Because as dry as it is, we're going to go on a journey together to make it less dry, to make it discernible, to make it understandable, to make probability and statistics, at least in this first series here, to make it our friend. We want to be friendly with this stuff. We want this stuff to be ingrained in our being. So, with that, let's look at countable additivity. That's a lot of numbers.
We have seen so far an example of a probability law on a discrete and finite sample space, as well as an example with an infinite and continuous sample space. Let us now look at an example involving a discrete but infinite sample space. We carry out an experiment whose outcome is an arbitrary positive integer. As an example of such an experiment, suppose that we keep tossing a coin and the outcome is the number of tosses until we observe heads for the first time. The first heads might appear in the first toss, or the second, or the third, and so on. So in this example, any positive integer is possible, and so our sample space is infinite. Let us now specify a probability law. A probability law should determine the probability of every event, of every subset of the sample space, that is, the probability of every set of positive integers. But instead, I will just tell you the probability of events that contain a single element. I'm going to tell you that there is probability 1 over 2 to the n that the outcome is equal to n.
Okay, we're slowing it down. This is a 12-minute long video. Okay, we're not going to slow it down. We're going to keep watching this. But I'm going to tell you right now, I'm already a little lost. But we want to chug through. We're going to come back in the next video and review this information, try to break it down. But I want to get to the Khan Academy stuff, so we're just going to let it ride.
Is this good enough?
But,
is this information enough to determine the probability of any subset?
We are given sample
Before
space
we look into that question, let us first do a quick sanity check to see whether these numbers that were given look like legitimate probabilities. Do they add to 1? Let's do a quick check. So the
check.
sum over all the possible values of n
The sum of over
of
all
the probabilities that we are given, which
sum.
is an
Hey, I know
infinite
that
sum
symbol.
from...
That's the sum symbol. That's the sum symbol right there. That's sum. See? We're getting smart. Hold on. I don't know if you... This one. Can you see it? Can you see my little mouse? This is the sum symbol. I feel like if I wrote this on a piece of paper, I'd feel really smart. For all of you people who actually took like advanced math in college or like high school, like you probably are familiar with this number. Every time I see this number, I feel like if I could just use that number, I would feel so smart about myself. Even if it just means like the sum of something, you know. Maybe I'm TMIing here, but every time I see it, I think smart things, you know, smarty pants things.
And go from starting from 1 all the way up to infinity of 1 over 2 to the n is equal to the following. First, we take out a factor of 1/2 from all these terms, which reduces the exponent from n to minus 1, or this is the same as running the sum from n equal 0 to infinity of 1/2.
Okay. Yeah, we can do that.
And
right.
to the n. And now we have a usual infinite geometric series, we have a formula for this. The geometric series has a value of 1 minus the number whose power we're taking, which is 1/2.
1/2, so 1 over 1
and
minus
after
1/2.
we do the arithmetic, this turns out to be equal to 1.
1.
So, indeed, it appears that we have the basic elements of what it would take to have a legitimate probability law. But now let us look into how we might calculate the probability of some general event. For example, the probability that the outcome is even. We proceed as follows. The probability that the outcome is even, this is the probability of an infinite set that consists of all the even integers.
All even integers. Okay, there exists some set that has all even
we
integers
can write
in it.
this set as the union of lots of little sets that contain a single element each. So it's the set containing the number 2, the set containing the number 4, the set containing the number 6, and so on. At this point, we notice that we're talking about the probability of a union of sets, and these sets are disjoint because they contain different elements. So we can use an additivity property and say...
Because isn't the set... So the set of 6 is just the set of 2, 2, and 2. That is 3 2s. That is the set of 6. The set of 4 is the set of 2 and 2. And the set of 2 is 2... Well, is the set of 1 and 1. 1 plus 1. I mean, these are mathematical operations, right? Fundamentally. I don't think that these numbers can exist in and of themselves, by themselves. They're always representative of something that's made up of something else, right? Like, isn't a 6 just 1 many times up to the limit of 6, and thus what we call several ones that make up 6. That is just a different name for the set of multiple ones that equal to 6. I suppose if we're representing it like lengthwise, if you go 1 space and you go 6 space, that is measurement, that is distance. If you were to go 1 and then you were to go to 6, those wouldn't be the same thing. But if you measured each point along the way, I don't know if what I'm saying is making sense. If you went from 1 to 2, that would be 1. If you went from 2 to 3, that would also be 1. The only thing that makes it 6 is that you start at one point and you go 1 6 times. That's measurement. So like, isn't the set of set things here that's happening, isn't that just like a similar thing? So we call it the set of 6, but that's really just the set of 1 1 1 1 1 1. I'm a thinker. I'm thinking. I don't know if that was just like a whole lot of rambling, and I said we would get through this, so...
That this is the probability of obtaining a 2, plus the probability of obtaining a 4
It's 208.
plus
We
the
gotta.
probability of obtaining a 6,
Telling you what.
and so on. If you're curious about doing this calculation and actually obtaining a numerical answer, you
We're going
would
a little
proceed as
faster.
follows. You notice that this is 1 over 2 to the second power plus 1 over 2 to the fourth power plus 1 over 2 to the sixth power, and so on. Now you factor out a
What'd he
factor
say?
of 1/4, and what you're
Okay.
left is 1 plus 1 over 2 to the second power, which is 1/4, plus 1 over 2 to the fourth power, which is the same as 1/4 to the second power, and so on. And now we have 1/4 times the infinite sum of a geometric series, which gives us 1 minus 1 over 1 minus 1/4. And after you do the algebra, you obtain a numerical answer, which is equal to 1/3. But leaving the details of the calculation aside, the more important question I want to address is the following. Is this calculation correct? We seem to have used an additivity property at this point, but the additivity properties that we have in our hands at this point only talk about disjoint unions of finitely many subsets. Our initial axiom talked about a disjoint union of two subsets, and then later on we established a similar property for a disjoint union of finitely many subsets. But here we're talking about the union of infinitely many subsets. So this step here is not really allowed by what we have in our hands. On the other hand, we would like our theory to allow this kind of calculation. The way out of this dilemma is to introduce an additional axiom that will indeed allow this kind of calculation. The axiom that we introduce is the following. If we have an infinite sequence of disjoint events, as for example in this picture, we have our sample space, we have a first event A1, we have a second event A2, a third event A3, and so we keep continuing, and we have an infinite sequence of such events, then the probability of the union of these events, of these infinitely many events, is the sum of their individual probabilities. The key word here is the word sequence. Namely, these events, these sets that we're dealing with, can be arranged so that we can talk about the first event, A1, the second event, A2, the third one, A3, and so on. To appreciate the issue that arises here, and to see why the word sequence is so important, let us consider the following calculation. Our sample space is the unit square, and we consider a model where the probability of a set is its area, as in the examples that we considered earlier. Let us now look at the probability of the overall sample space. Our sample space is the unit square, and the unit square can be thought of as the union of various sets that consist of single points. So it's the union of subsets with one element each, and it's a union taken over all the points in the unit square. Then we think about additivity. We observe that these subsets are disjoint. If we're considering different points, then we get disjoint single element sets. And then an additivity property would tell us that the probability of this union is the sum of the probabilities of the different single element subsets. Now, as we discussed before, single element subsets have zero probability, so we have a sum of lots of zeros, and the sum of zeros should be equal to 0. On the other hand, by the probability axioms, the probability of the entire sample space should be equal to 1, and so we have established that 1 is equal to 0. This looks like a paradox. Is it? The catch is that there is nothing in the axioms we have introduced so far, or the properties we have established, that would justify this step. So this step here is questionable. You might argue that the unit square is the union of disjoint single element sets, which is the case that we have in additivity axioms, but the additivity axiom only applies when we have a sequence of events. And this is not what we have here. This is not a union of a sequence of single element sets. In fact, there is no way that the elements of the unit square can be arranged in a sequence. The unit square is said to be an uncountable set. This is a deep and fundamental mathematical fact. What it essentially says is that there are two kinds of infinite sets: discrete ones, or in formal terminology, countable. These are sets whose elements can be arranged in a sequence, like the integers. And also uncountable sets, such as the unit square or the real line, whose elements cannot be arranged in a sequence. If you're curious, you can find the proof of this important fact in the supplementary materials that we are providing.
Okay.
After all this discussion, you may now have legitimate suspicions about the models we have been looking at. Is area a legitimate probability law? Does it even satisfy countable additivity? This question takes us into deep waters and has to do with a deep subfield of mathematics called measure theory. Fortunately, it turns out that all is well. Area is a legitimate probability law. It does indeed satisfy the countable additivity axiom, as long as we only deal with nice subsets of the unit square. Fortunately, the subsets that arise in whatever we do in this course will be nice. Subsets that are not nice are quite pathological, and we will not encounter them. At this stage, we are not in a position to say anything more that would be meaningful about these issues because they're quite complicated and mathematically deep. We can only say that there are some serious mathematical subtleties, but fortunately they can all be overcome in a rigorous manner. And for the rest of this class, you can just forget about these subtle issues.
Oh, thank goodness. I don't have to actually learn hard things. That's great. That means I can say I learned things without actually knowing them. To be fair, I mean, we're just in this to like learn mostly the basics. I mean, we want to get advanced, right? We want to get as advanced as we can go. But well, there's only so many hours in the day, right? So many hours in the day. So if I had to summarize what I just learned, is basically sometimes when it comes to continuous situations, like with the unit square, which is how we determine probabilities within the unit square, which represents the set where there's subsets, it can appear to be a paradox, and due to some jargon, like it can seem like 1 equals 0, but I mean, if I'm honest, like I can't really say that I understood what I just saw. Something about a set that some math equals some other math. Clearly, I'm comprehending this. But hey, like I said, we're just trying to crush through this. And this one looks like it'll be fun. It's interpretations and uses of probabilities. So I'm going to put this on, and I'm going to go grab a snack. But it's going to be running in the background. And then we're an hour and 6 minutes in. After we're done with this video, we're going to Khan Academy. I've got the course right here. This is like, I gotta change here. We're changing my nickname to Mind of Meaning. That's the proper name, okay? We're saving that. Oh my goodness. Okay. Give me a second. One moment, please. All right. All is right with the worlds. But before we get to this, I'm going to put this other video on, and I'm going to go grab a snack and be right back.
We end this lecture sequence by stepping back to discuss what probability theory really is and what exactly is the meaning of the word probability. In the most narrow view, probability theory is just a branch of mathematics. We start with some axioms, we consider models that satisfy these axioms, and we establish some consequences, which are the theorems of this theory. You could do all that without ever asking the question of what the word probability really means. Yet, one of the theorems of probability theory that we will see later in this class is that probabilities can be interpreted as frequencies. Very loosely speaking, if I have a fair coin and I toss it infinitely many times, then the fraction of heads that I will observe will be 1/2. In this sense, the probability of an event A can be interpreted as the frequency with which event A will occur in an infinite number of repetitions of the experiment. But is this all there is? If we're dealing with coin tosses, it makes sense to think of probabilities as frequencies. But consider a statement such as, the current president of my country will be re-elected in the next election with probability 0.7. It is hard to think of this number 0.7 as a frequency. It does not make sense to think of infinitely many repetitions of the next election. In cases like this, and in many others, it is better to think of probabilities as just some way of describing our beliefs. And if you're a betting person, probabilities can be thought of as some numerical guidance into what kinds of bets you might be willing to make. But now, if we think of probabilities as beliefs, you can run into the argument that, well, beliefs are subjective. Isn't probability theory supposed to be an objective part of math and science? Is probability theory just an exercise in subjectivity? Well, not quite. There is more into it. Probability, at the minimum, gives us some rules for thinking systematically about uncertain situations. And if it happens that our probability model, our subjective beliefs, have some relation with the real world, then probability theory can be a very useful tool for making predictions and decisions that apply to the real world. Now, whether your predictions and decisions will be any good will depend on whether you have chosen a good model. Have you chosen a model that provides a good enough representation of the real world? How do you make sure that this is the case? There is a whole field, the field of statistics, whose purpose is to complement probability theory by using data to come up with good models. And so we have the following diagram that summarizes the relation between the real world, statistics, and probability. The real world generates data. The field of statistics and inference uses these data to come up with probabilistic models. Once we have a probabilistic model, we use probability theory and the analysis tools that it provides to us, and the results that we get from this analysis lead to predictions and decisions about the real world.
That's where that ended? I mean, I appreciate it. It was cool. But I kind of thought we were gonna... I was liking it. If you don't remember, we started reading the Stanford Encyclopedia of Statistics. And it sort of covered some of those things. Sorry. The Stanford Encyclopedia of Philosophy on the Philosophy of Statistics. Jesus. Anyway, so we were reading that, and they sort of covered like two different ways of interpreting probability and statistics in terms of like, well, are we saying something about the actuality of the real world, or are we saying something about the our beliefs about the real world, and how those two different ways of thinking about it, basically Bayesianism versus classic thinking about it, are what exists. Both have their arguments, right? Do I understand them very well? No. But that's what we're doing here. That's what we're doing here. And guess what? We finished the first section. We will definitely cover the supplemental material, but we are moving on to Khan Academy because I said that we would. And we're obviously not going to finish this, but we are going to look at it. So let's get an overview of the course here. Okay, so here I am on Khan Academy. You will see what we have here. We've got the Khan Academy logo. We got the begging for more money, which reminds me, if you want to support my work, please go to patreon.com/mindofmeaning and contribute only the small, tiny amount of $5 over month. That's $5 every 28 to 31 days. Just $5. Okay? Mathematically, like if I bring up my calculator, like what was I gonna do? I was gonna do like, okay, so you have $5, right? $5. All right, that's we have $5, right? Let's divide $5 by 28 days, right? So what do we have? That's 18 cents a day. 18 cents. 18 cents a day. That's nothing. Do you think you could give me 18 cents a day? That's all I'm asking for. Just imagine I showed up in your world and you're like, hey, can I borrow 18 cents? And imagine I said that every day, you know? I mean, yeah, it would get annoying, but then I was like, look, I normally ask you for 18 cents a day. Maybe you could just give me a $5 to hold me over for the month. That's all I'm saying. 18 cents a day. I keep gesturing towards the computer. I understand the camera's over there. Okay. I know it's very attractive watching me eat. Look, I'm hungry, okay? So we're going to take an overview. Look, if we look at the side here, we've got 16 units. 16 whole units. And if I click on one of these, what happens? Well, it brings me to a different, it brings me to that units page, right? So it doesn't expand. I was kind of expecting it to expand, but it's not expanding. It's just brings me to the page. But we've got analyzing categorical data, displaying and comparing quantitative data. We've got summarizing quantitative data, modeling, exploring, study design, probability, counting permutations, random variables, sampling distributions, confidence interviews, significant tests, two-sample inference for the difference between groups, inference for categorical data, advanced regression, and analysis of variance. We're starting way at the beginning, analyzing categorical data. If you remember from the information that we've looked at previous episodes, categorical data is the kind of data that isn't numerical data. That is, it is data that has its own sort of unique category, but it isn't. Well, it's nominal. Is that how they're using it? I think they mean nominal when they say categorical, but we will find out as we read or as we watch more. So we are starting on Unit 1, analyzing categorical data. This unit covers analyzing one categorical variable, a quiz, two-way table, quiz 2, distributions in two-way tables, quiz 3, and a unit test. That's what we got to get through. Will I get through it all today? No, I'm not going to try and make it through today. But we are going to take it step by step. We're going to watch Mr. Khan here and see what we can learn. Okay? Let's learn. Let's start our learning journey. Thank you for joining me. All right. Mr. Khan, let's see where we can go.
We're told that millions of Americans rely on
man
caffeine
himself,
to get
huh?
them up in the morning, which is true. Although, if I drank caffeine in the morning, I'm very sensitive. I wouldn't be able to sleep at night. Here's nutritional data on some popular drinks at Ben's Beans Coffee Shop. All right, so here we have the different names of the drinks. And then here we have the type of the drink, and it looks like they're either hot or cold. Here we have the calories for each of those drinks. Here we have the sugar content in grams for each of those drinks. And here we have the caffeine in milligrams for each of those drinks. And then we are asked, the individuals in this data set are, and we have three choices: Ben's Beans customers, Ben's Beans drinks, or the caffeine contents. Now, we have to be careful. When someone says the individuals in a data set, they don't necessarily mean that they have to be people. They could be things. And the individuals in this data set, each of these rows, they're referring to a certain type of drink at Ben's Beans coffee shops. So the different types of drinks that Ben's Beans offers, those are the individuals in this data set. So they're Ben's Beans drinks. Next, they ask us, the data set contains, and they say how many variables and how many of those variables are categorical. So if we look up here, let's look at the variables. So this first column that is essentially giving us the type of drink, this wouldn't be a variable, this would be more of an identifier, but all of these other columns are representing variables. So for example, type is a variable. It can either be hot or cold. And because it can only take on one of kind of a number of buckets. It's either going to be hot or cold. It's going to fit in one category or another. And you don't just have two categories. You could have more than two categories, but it isn't just some type of variable number that can take on a bunch of different values. So this right over here is a categorical variable. Calories is not a categorical variable. You could have something with 4.1 calories. You could have something with 178. Things aren't fitting into nice buckets. Same thing for sugars and for the caffeine, that these are quantitative variables that don't just fit into a category. And so here I would say that we have 4 variables, 1, 2, 3, 4, one of which is categorical. So that would be choice A over here.
Oh man, it's like being back in high school again. Regaining my youth. Oh goodness me. Okay, let's go to the next one. Ooh, what is this? Am I already taking a test? Ready to practice. Oh yeah, let's go. Millions of Americans rely on caffeine to get them up in the morning. I know I do. Here's nutritional data on some popular drinks at Ben Beat's coffee shop. Type calorie, sugar, caffeine. The individuals in this data set are, choose one. It's gonna be the drinks, obviously. Didn't he just go over this? It's just starting us off slow, you know? All right. Maybe has my mic been too quiet? I don't want to peak too much, but I don't want you to not hear me either. Beautiful people who I love dearly. Okay, this data set contains 4 he just gave me this answer. So 4 variables, one of which is categorical. Okay, check. Oh my goodness! I answered the answers correctly that he already answered. Go me. Okay, but okay, new stuff. Challenging. The girls' basketball team played a game this Wednesday. Here are some statistics for the players from the game. Player name: Simone, Marisol, Darren, Ali, Asha. Percentages. Asha's really messing up, huh? Assists. Asha, what's wrong with you? Oh, you're a sophomore, that's why. The individuals in this dataset are the basketball players. This dataset contains, we've got class and we've got player name, which are the 2. We've got 4 variables. 5? Why is it saying 5? 1, 2, 3, 4. I'm seeing 4. Am I crazy? Is there like a 1, 2, 3, 4? Quantitative, 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 quantitative. Well, there's 2 quantitatives. So it's one of these 3 variables. Oh, I get it. Oh, man. Okay, so yeah. There's 3. Right, and these are not variables, these are the individuals, right? So it's 3 variables, 2 of which are quantitative. Ha ha ha, very funny. Listen, okay, I was a little my caffeine's wearing off, okay? Camille is comparing different apartment complexes. Here's the data she has collected. Complex. 1, 2, 3, 4. The individuals in the data set are the apartment complexes. We have 1, 2, 3, 4, 5 variables. I feel like you could consider this quantitative if you were to code these as a 1 or a 0. But I think for the sake of this question, it's going to be 5 variables, 2 of which are qualitative or 3 of which are quantitative, categorical. See? 1, 2, 3, 4, 5. It's 5. Yeah, 5. 2 of which are categorical. So you don't even give me the chance to make a wrong answer. Because it would either, if this were nominal or quantitative, then it would be 4, not 3. So yeah, I'm perfect, as usual. On to the next one. Student names. We're back in class. We have 3 categorical variables. The individuals are college students. We have 3 variables, 3 of which are categorical. And it's that simple. I make it look easy. I make it look easy. I leveled up. Look at me. Look at me go. I'm a genius. Wow.
According to the pictograph below, how many survey respondents have type O positive blood? How many have O negative blood? So a pictograph is really just a way of representing data with pictures that are somehow related to the data. So in this case, they give us little pictures of, I'm assuming, blood drops right over here. And then they tell us that each blood drop in this pictograph represents 8 people. So you can kind of view that as a scale of these graphs. Each of these say 8 people. So for example, if you say how many people have A positive, it would be 1, 2, 3, 4, 5, 6, 7 blood drops. But each of those blood drops represent 8 people. So it would be 56 people have type A positive. But let's answer the actual question that they're asking us. How many survey respondents have type O positive? O positive. So this is O, and then we care about O positive. So we have 1 blood drop, 2, 3. Let me do this in a new different color. We have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 drops. I'll put those in quotes because pictures of drops. And then the scale is 8 people. 8 people, let me write it this way, times 8 people per drop. 8 people per drop. And so 8 times 8, and actually even the drops, you can view them as canceling out if you view them as units. So drops. 8 times 8 is equal to 64 people. So they could have written literally the number 64 right over here. 64 people have type O positive blood. Now let's think about the O negative case. O negative blood. Well, this is O, and then within the blood group O, this is O negative, and we have 1 drops, 2 drops. So we have 2 drops times 8 people per drop. 8 people per drop. And so 2 times 8, each of these represent 8. So 8 and then 16, or 2 times 8 is equal to 16 people. So 16 of the survey respondents, 16 have type O negative, 64 have type O positive.
I definitely paid attention. Okay. Up next, exercise. I do need to exercise. Ready to practice. Ready to practice. Peeking out my microphone. I saw myself, was so alone. But now I'm on to the next thing. Let's see what this old world can bring. You like my little rhyme? The picture graph below shows the number of squirrels participating in the different dance classes. What? Tap, ballet, jazz, and the hip hop. How many squirrels are in the tap and ballet combined than in hip hop? Okay, so hip hop has 4 or has 5. I can math. Ballet, tap has 4, 5, 6, 7. So that's 2. 2 more squirrels. If I'm understanding this question, if I'm understanding this question correctly, it says, how many more squirrels are in tap and ballet combined with hip hop? Obviously, that's 2. Look at how genius I am. Not quite. What? Wow. Look at me just putting this out into the world. How many more squirrels are in tap and ballet combined than in hip hop? What? Hip hop. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Is my stuff is getting flickery again. I hate when it does that. Might be time for a reboot. Okay, so are they just asking me for the total? 4, 5, 6, 7. 7 squirrels. Come on, 7 squirrels. Is that it? Give it another shot. Tap and ballet. Hip hop. 1, 2, 3, 4, 5. Wow. Wow. Okay, what did I miss? Dude, I'm so mad. Like, I must have missed something. You know, I come online to feel like a genius, and I'm getting defeated by freaking Khan Academy because I'm misunderstanding something stupid and basic. So, oh,
Jacob charges $9 an hour to paint.
That's
the
right.
graph
Talk to me
below
like
shows
I'm
the number of
stupid.
hours he spent
Thank
painting
you.
different rooms of one house. How much did Jacob charge for painting the living room?
Oh, I love it.
So here's the graph. This is a picture graph or pictograph.
Okay.
And it shows us how much time Jacob spent painting different rooms of a house.
Got
One
it.
super important thing is this little key right here that tells us each of these paint buckets is 3 hours of time. So,
Oh, that's what that means? Okay. Wow. Stop flickering. Okay, so one little symbol equals 5 square. Wow, I just totally flew over my head. Okay, so this is actually, this is 25 squirrels. This is 20 squirrels. This is 15 squirrels. So 20 plus 15 is 35. That's 10. The answer is 10. Okay, look. What did I say? My coffee's wearing off. Look, I got it. I'm back to being a genius. I'm back at it. This is the importance of reading directions, kids. And reading them well. Or you'll make yourself look like a fool on the internet. Luckily, none of you are watching, and if you are watching, please consider going to patreon.com/mindofmeaning and contributing $5. That is 18 cents per day, but in the form of $5 per month to this content, which is clearly the best value that has ever existed on the planet. Okay? Consider it. Here we learn useful things. Here we learn how to interpret the structure of reality. Here we learn how to make ourselves look like a fool on the internet because you can't read a graph. So, if you pity me, then please consider donating $5 per month. And if you hate that flickering that's going on my screen, then join the club. I don't know why you're flickering. Stop it. Stop it. Stop it. Here's what I'm gonna do. I'm gonna... I don't know why it gets flickery. It doesn't happen. Oh, okay. Okay. Oh, it's another one. Okay, sorry. It's just in the zone. Some students at Darren's school signed a petition asking for a reading area for recess. The graph below shows the number of signatures from each grade. Aw. That's right, kids. Get political. 2 signatures. How many total signatures are on the petition? What do we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So 20 times 2 is 40. I'm a genius. Mary has 50 pages in her notebook. You're killing me. You're killing me. Okay. Hold on. Hold on. Hold on. Hold on. I'm just gonna do that. Okay? I'm not gonna... Do you remember this screen from like your childhood, if you're my age? If you don't know how old I am because of my boyish good looks, I'm 34. Can you believe that? 34. Of course you can believe that because you don't really even know who I am. But it's pretty strange to be 34. It's just kind of like being 28, just different. Okay. All right, so we're plugged back into the matrix here. I'm going to see if I can get my thing to do the thing. Hello? Okay. I think I can fix it. I think I can fix it. We're gonna just click away. Well, now there's 2 of me. Okay, then we're gonna click back. I think I can fix it. Did I mess it up forever? Is this gonna be like this forever? Those are your grandpa's memes. Hello? Oh. What if I go here? There, back, here, there. I'm so upset. We were doing so well. Okay, maybe if I... and now... Everything is just going wrong. Hold on. God, hold on. Okay, we can We can bring it back. Okay. I'm back. Well, friends, this is probably the end. This is what happens when you buy a cheap capture card. You run into issues like this. All things considered, it's done pretty well. I bought this stuff some time ago. Okay, well, I guess that's it. Did you have fun, guys? Did you have fun watching me be a fool? Trying to succeed at this content. Where am I? Where did I go? I thought I had a picture of me over here. Hold on. I'm trying to. I'm gonna click that. Oh, there I am. There's my face in all its glory. And there's the weird face guy. Yeah. All right. Cool. Anyway, we did our best. I know I could set this up. So my situation is I have two laptops kind of set up to do this stuff, and sometimes my OBS messes up and gets all flickery, and then I get annoyed with it, and then I end up screwing the whole stream. So, oh, and my CPU over here is like a bajillion degrees. I don't know why that is. It's weird. I'm not sure why that's happening. So what we're going to do is we're going to end it here. We're going to call it. It's been an hour and 42 minutes. So I want to just thank you all for joining me. If you enjoy this content, please consider going to patreon.com/mindofmeaning. I'm probably going to go get some more food or a drink or something. Try to plan out the content better next time. But we did get through some Khan Academy, and oh man, the memories we've created. Me not being able to count squirrels. All right, but the squirrels won't get us again, okay? The squirrels will not get us again. In the meantime, I hope you have a fantastic day. I hope it's the best day of your entire life, better than any future day and any past day, because you deserve it. Treat yourself, okay? Have a fantastic day. Until we meet again, which may be in a few hours or maybe in a few months, probably just in a couple days. Until we meet again, have a great night, and remember, I need a good outro. If any of you are ever going to be here and have any ideas for an outro, let me know. Just leave a comment, leave a message, leave a text. Okay? Just give me some ideas. And other than that, I will see you next time. On the Mind of Meaning channel. Bye.